let's start our last talk of today's sessions. The speaker is Khadim. Khadim is a professor at IMPA, and he obtained his PhD at ICTP under the orientation of Stefano Lusato. He has realized several postdocs, the last one at University of Chicago, and today he's going to talk about classic geodesic on surface without conjugated points. Thank you, Khadim.
Thank you, Karina, for the introduction. Thank you, the organizers, especially Yuri, for this nice invitation. It's really a pleasure to talk about this result here for me, though I have been talking about it for the last few months. So it's something I really like I enjoy talking about, and yeah. So the talk is about closed geodesics on surfaces without conjugate points. And everything I'm going to talk about is a joint work with von Klemanaga and Gerhard Knipper. So this is a general problem counting closed geodesics. So what I will have first to do is to just tell you like what the problem is in this setting, because maybe not everybody is familiar with surfaces without conjugate points. I'm just going to tell you now what comes with this condition. Maybe I should do this. Yes. So during this talk, I suppose that the talk will be on surfaces. Do the results hold in higher dimension with many conditions that I don't want to get into those conditions. In 2 dimension, we don't have just without the surface without conjugate points is enough for our results. Okay. So see that, okay, so I don't want to zoom in. So I'll be supposing that I have a Riemannian manifold. So M is a 2-dimensional, I'm used to zooming in when I write. So this is a 2-dimensional closed surface, okay? And this is a Riemannian metric. G is a Riemannian metric. So the problem is we are counting closed geodesics. First of all, geodesics are just shortest path with respect to this metric, okay, that is given. So geodesics are shortest with respect to the metric, okay? Joining points. Okay, now what is a closed geodesics is, a loop. So a closed geodesic C from R to M is closed geodesic if there exists some time t, which is a multiple of the period, such that Ct plus t equals C of t, for all t in R. So this is a loop that is like a geodesic. So the problem interesting here is we are counting these closed geodesic, these closed loops. And so the setting we want to consider is a surface without conjugate points. So before I go to the definition of conjugate points, let me just tell you that this is beyond the negative curvature. What I want to say is that, like, you can think of a surface of this type. I'm not very good in drawing this stuff, but think of a surface of this type where here you have a negative curvature here. You have here a negative curvature part here also, but here is flat. The curvature is 0 in this middle, this neck here. So the surface we will be considering, they will include this type of surface. So to make sense of the counting, we need to, to say really what we are counting, because if you consider this neck, you have like uncountably many closed geodesics on this neck. For instance, here, you have many. In this part, you have many closed geodesics. All of these are like uncountably many of them. These are closed geodesics. So when we say counting in the setting that I'm going to consider, I'm counting the free homotopy classes. Like all these closed geodesics in this neck, they consider one. They are considered as one because they are all free homotopic. Okay. So given T positive, so this is non-positive curvature. What we are saying is beyond this. So for T positive, we let PT be the number of free homotopy classes with a closed geodesic of lengths at most T, with a closed geodesic of lengths less or equal to T. Okay. I mean, just know that if you have only negative curvature, every free homotopy class will have only one closed geodesic. You can think of like, even if you just assume expansivity, like if the flow is expansive, you cannot have two closed geodesic in the same free homotopy class. But in the setting that we're considering, we might have multiple guy in the same class. So this study, it goes back to Haber in the 1959. He proved like the asymptote, the counting for these closed geodesic in negative curvature, like constant negative curvature. When the curvature is constant -1, Haber proved in 59 PT, like this number, it goes like ET over T. He said that this asymptote is like ET over T. And yeah, so this Haber's proof is really, it highly rely on the constant negative curvature, on the fact that you have like a symmetric, like it's like a symmetric space, because it relies on the relationship between the Mach length spectrum and the spectrum of the Laplacian. And that relationship, you only have it when the surface is like locally symmetric. So yeah. So what we are going to talk about is beyond negative curvature, though negative variable curvature was also done later. I will tell you what is known after. But this was the first results on constant negative curvature. Let me just now define what no conjugate points mean. Like no conjugate points or conjugate points. So yeah. So to do that, I like to use a definition using Jacobi field. It has many, there are many ways to define it, but the way using Jacobi field, I like it because it's something that allows you to do calculation, to exercise a little bit. So given a geodesic C to M, take J from R to TCM. So I just write TCM to mean the tangent to this geodesic. Okay, is a Jacobi field. If it satisfies the following, it's a simple, first order, a second order linear ODE, like J double prime plus K C of T, J of T equals 0. So this is the Jacobi equation, and I like this formula because this is two-dimensional, and I'm only considering transverse Jacobi fields to the geodesic flow, and I can think of it as just like a function. And this derivative is a covariant derivative. In higher dimension, instead of this curvature, you will have the curvature tensor, okay? But I'm just two-dimensional, okay? And 2 points are conjugates. 2 points, CT1 and CT2 are conjugate if there exists a Jacobi field is J to M Jacobi field, I write this as Jacobi field, okay? Says that J at T1 equals J at T2 equals 0, but J is not identically 0, okay? It's not identically 0. Let's say this is what you would think of, like you have here your geodesic, this is C of T1, and this is C of T2, and you have a Jacobi field that start being 0 at T1 and start growing, is growing a little bit and start decaying, maybe grow again and decay and go to 0 again. So if you have this type of picture, these 2 points are conjugate. Think of like, you know, if you have a metric on the sphere, you know, you have many of these conjugate points there. But let me just tell you that if you have negative curvature, you don't have already non-positive curvature. So remark, this is not very difficult to prove. So remark is that non-positive curvature implies no conjugate points. Okay, no positive coverage implies no conjugate points. I mean, the proof is not very difficult. You can just think, you can just prove when you have non-positive curvature, you can just prove that the norm of the Jacobi field is convex. Okay, the Jacobi field is convex. Yeah, so you cannot have vanishing at 2 points unless it is 0 everywhere. Okay, so I would tell them, so I should say the reverse here is false. Like no conjugate points doesn't imply non-positive curvature. Okay, there is an example by Burns, like this dinosaur example, where you don't have conjugate points.
Khadim, I think that
implies, so this is
your connection freeze for a moment.
Oh.
So it's better if you repeat the last 2 seconds. Sorry. Okay. Can you hear me?
Yes, I'm hearing you.
Now it's okay.
I'm sorry. So I was saying that the reverse of this remark is false. There's an example by Burns, because what you should know is that non-positive curvature implies what we call flat strip theorem. Flat strip is just this neck that I draw. Like if you have 2 closed geodesics that stay at a bounded distance for all time in the universal cover, so they bound a flat strip. That is true in non-positive curvature, but it's not in general true if you just have no conjugate point. So the reverse is true. So no conjugate point is more general than non-positive curvature, okay? So our theorem here is Klimanaga and Knipper, myself, is that if you have MG closed surface without conjugate points, and of genus at least 2. I'll tell you why we need this genus, okay? Of genus at least 2, then we have that PT goes like, oh, I should not say equal. It goes like e to the HT over HT, where H here is the topological entropy of the geodesic flow, where H is topological entropy of the geodesic flow, okay? geodesic flow. So yeah, so this is our results. So it has few conditions, like the genius, just to ensure that the entropy is positive, the entropy of your system. Okay, because if you have a genius at least 2, that means you have a background metric of negative curvature. And if you have a background metric of negative curvature, we know that that metric has positive entropy, and there is a the relationship between the two entropy using this this Freire-Magnier or Manning formula of the entropy. Okay, yeah. So yeah, so that's maybe the only condition. The genius, and yeah, it's not a condition, because genius 1, we know this the torus cannot have like if the torus, the metric without conjugate points on the torus is just the flat metric, and we know flat metric, we know the closed orbit, we know. Okay, so let me just tell you the different bounds that were studied in the literature. So there were 3 different bound for this closed geodesics. So there's what is called the exponential graph, which I call EG. So this is just telling you that the closed geodesic, they glow like the entropy. So this is just limit when t goes to infinity of 1 over t log of pt equals h. And beside that, there is also the uniform bound. So let's call it UB. So this is just telling you that you have constant A and B, just that you have, sorry for not being constant, like consistent in this T. Sometimes I write big T, sometimes capital T, sometimes small t. I'm sorry about that. That's not very consistent. B over T, E, H, T. Okay, this is the uniform bound. Now there is the optimal bound, which is a multiplicative asymptote, or the Margulis estimate multiplicative asymptote. Is that MA? So what does it say? It just says that this limit is 1, like the limit, like B and A in the uniform bound, they tends to 1, they tends to something like 1 over H, okay, when T goes to infinity. Or you just have limit when T goes to infinity of PT over EHT over HT is 1. Okay, so this is the optimal bound that you can get. Okay, well, you can discuss after the rate of convergence, but that will have really something to do with the rate of mixing of the measure of maximum entropy. And for this system, we could not get any rate of mixing. Okay, so as I said in the beginning, there is this work by Haber in 59. We did it in constant negative curvature. Haber proved MA, okay? Haber proved MA 59, okay? 59, so I should write this. And then later there is a result by Sinai in 1966. So this gives UB, the uniform bound for geodesic flow in variable negative curvature. So this is variable negative curvature, okay? No restriction on dimension, no restriction on, like, this the curvature should be negative, okay? And later, I mean, a few years later, there's this thesis of Margulis. Margulis did it in his thesis, 1969. He did the multiplicative asymptote for any topologically mixing anodes of flow, which includes the geodesic flow, okay? The geodesic flow in negative curvature. So topologically mixing annals of flows. Okay. Yeah. And also there is a result of Parry and Polycott also, I should mention. Parry and Polycott in 1983 for axiom A flows. Okay, they also proved this multiplicative asymptote for axiom A flows. And there are also some results beyond negative curvature. So beyond negative curvature, So there is the result by Khadim. He proved that if the entropy is positive, smooth flow, no fixed point, you have EG. So Khadim in 1982. So smooth flow with positive topological entropy and no fixed point, okay? No fixed point. So he proved the exponential growth, okay? The growth like entropy, the close of it. And also there is recently a result by Yuri Lima and Omri Sarik in 3D, 2019. So there is Lima and Sarik in 2019, I think, yes. So they proved the uniform bound for 3-dimensional flow with positive entropy. So UB for 3D flow, just that the entropy has to be positive, okay? Yeah, I think that's what it is.
Also no fixed point.
Oh, no fixed point also, yes, thank you. Yes, it's good to have the authors when you are giving these talks sometimes. No fixed points. Yes. Yes. Thank you. And also there is a result by Knipper that I should cite also, which is beyond negative curvature, non-positive curvature in rank 1. So Knipper in 1983, he did it for rank 1. Rank 1 gives EG, exponential growth. And there is a very recent preprint by Russell Ricks, who did it for rank 1 in cut-zero spaces, which generalizes the non-positive curvature but to cut-zero spaces, which is a little more general. So Ricks in 2019. So rank 1, as far as I know, it was a preprint. I don't know. Yeah, it is on the archive. Cut-zero space. He proved the multiplicative asymptote actually. And actually our idea is based in many arguments, in improving our theorem, many arguments that was given by Russell Ricks. So for the time I have now, I will try to explain you the ideas of the proof. So this is the theorem. It tells you that you have the exact, this asymptote, the Margulis asymptote for the closed geodesics in non-conjugate points. And yeah, this is what is known so far. So now the next part of the proof of the presentation, I want to tell you about ideas of the proof. Okay. So I should say the proof it relies on three main points. So one, first thing that we need to use is that the measure of maximal entropy has a product structure, okay? Because if you're, yeah, so the idea is close to Bowen's, Margulis argument, which is you have this box, which have some nice transversality between stable and unstable, and you have nice decomposition of the measure of maximum entropy into stable and unstable. So we also need that type of argument here. So we need the fact that the measure of maximal entropy, has a product structure. Entropy has a product structure. So this is actually something we got it from the construction of the measure of maximum entropy, because in our first paper with Vaughan and Gerhard, we construct the measure of maximum entropy via Patterson-Sullivan measures, and that construction, the product structure, it comes naturally with that construction, okay? So we didn't have to do that in this paper. And also, we have it already in our construction in the previous paper. We have that the flow is mixing, yeah. So whoever knows like this Margulis instrument knows that mixing is something you need, and I will tell you how it is used here. The geodesic flow, I'm sorry, I'm calling it a name, but I haven't introduced the name yet. So the geodesic flow is mixing. Is mixing with respect to the measure of maximum entropy. Let me call it a name here, measure of maximum entropy. Let's call it M, okay? Geodesic flow is mixing with respect to M. Okay, mixing, you know what it means, like the measure of, you know, the hit rate of one set intersect the other one is converging to the product of measures. And another point which is very interesting, which is very important, is that we have equidistribution of closed geodesics. This is just something you get actually from EG, like the fact that EG, yeah, so let me tell you, equidistribution of closed geodesics. Like this is saying that if you take a distribution based on closed geodesic of length t, when t goes to infinity, this is converging to a measure of maximum entropy. So of course you will need uniqueness of the measure of maximum entropy, but that's something also we have in our first preprint. So these are the three main steps. So let me now tell you how these steps are used. So first of all, to count these closed geodesics, we wanna, you know, shift the problem a little bit, counting closed geodesic to counting elements of the fundamental group, okay? Because there is a nice relationship between I mean, it's a type of a closing lemma that we prove here between the closed geodesic and elements of the fundamental group. So let's just use some notation now. M tilde, so is a universal cover, okay? Universal cover, okay? And that, let's call gamma, which is pi 1m, the first fundamental group. So which is like a subgroup of the group of isometries of M tilde. So this is acting like the elements of the fundamental group are acting like isometries, okay? That's something maybe I don't need to say how is that. So it is easy to see that. So for every closed geodesic correspond to every closed geodesic C correspond to a certain gamma C on gamma. How is that? So this and it's not trivial, okay? This is not trivial. This is not trivial. Yeah, because this is simple. Like if you have a closed loop, and this loop is not trivial, so it has it corresponds to a fundamental group, so it corresponds to an element, okay? And also there is also this also correspondence. So every gamma in gamma, I'm just telling you there is a bijection between these two. like, I don't want to say bijection because I did not define properly what these two sets are, because there are powers of elements of the fundamental group, like there are prime and stuff. I don't want to say bijection, but I'll just tell you, I'm just trying to tell you how we shift this problem from counting closed geodesic to counting some elements of the fundamental group. Every gamma in gamma, non-trivial, so there exists C from R to M tilde. So I'm lifting everything to the universal cover, such that gamma C equals C. Okay, and in particular this C gamma, let's call it C gamma. So I said gamma acts on the universal cover as isometry, so gamma C is again a geodesic. So now for every gamma you have this correspondence, like correspond to, and this guy is closed. Okay, C gamma is closed because of this relationship. It's closed. Okay, and see that here the length of the gamma, or the period, if you want, I haven't defined it, but I'm sure we are familiar with it. A period or a multiple of the period is just the distance. Yeah, and there is here what we called, I don't have too much time, but I will try to say this. What I'm trying to say here is that if you have this equality here, that means that there is T, but it says that gamma CT equals CT plus T. Okay, C gamma. Okay, C gamma. This is the corresponding geodesic to gamma, and this T is called the size of gamma. Okay, and it has to do with the period. Okay, so this is some, like, this is general. Okay, this doesn't use anything new. You can find the proof in many textbooks, like for this fact here, the fact that every gamma there is a closed geodesic that is invariant. And so, yeah, now the main one thing that we needed to do here is to prove a type of closing lemma. Like if you have a recurrent geodesic, there is a geodesic nearby that is closed. That in hyperbolicity, you don't have any problem doing that because you have all the, you have all the uniform hyperbolicity that you need to do the type of closing lemma that you want. But in this setting, you don't have enough hyperbolicity. You don't have exponential contraction of stable and unstable, set. So what we prove, what we call here closing lemma, is that we consider a set B. I will not be very explicit in this set B unless the time allows or there are questions. So think of this set B being like a epsilon thickening of something. So in this direction, it is like epsilon, okay? In this direction, it is like epsilon. This is the flow direction, okay? This is the flow direction, this epsilon. And think of these guys are like plaque that are like, one is foliated by stable, okay? And this is just a box. This is what Margulis constructed, this box. So, and the idea is now to count the number of closed geodesics through this box of length T. So number, I will not be explicit in constructing this box unless closed geodesics through B of length less than T. We call this set of length less than T. We call this set gamma C T, okay? I will not put B here in this notation. It would be heavy. I'm just working with a set B after to generalize it to the manifold. So the closing lemma here, it tells you that there's a bijection between this set, and there's a one-to-one correspondence between the geodesic through B of length T and this set gamma T yeah, if I write it, you will really see that this is just a type of a closing lemma, because you will see recurrence equals the set of gamma in gamma for which B intersect with. So gamma star is a push forward because I did not say F minus T. Okay, I should put capital T. I will tell you what these quantities are. F minus T, B is not empty. I'll tell you what these quantities are. So F is a geodesic flow, okay? F here, this is a geodesic flow. So the geodesic flow Ft is acting on the unitarian bundle, okay? T1M. I consider the lift, so T1M tilde, okay? T1M tilde, okay? So gamma is acting on the, so gamma star is acting on the unitarian bundle as well, because it's an isometry. So see that, what does this mean? This set not being empty, it means that there is a recurrence, right? There is a recurrence. So this is just, if you think about it twice, you see that this is just recurrence. Recurrence. And saying that there is a one-to-one correspondence between these two sets, one way is just the closing lemma. That means that recurrence implies that there is a closed geodesic nearby. Okay, so this is this one-to-one, oops, is just, this is a closing lemma. How much time do you have?
3 minutes.
3 minutes, wow. Closing lemma. So yeah, so we proved this. I will not go into the proof, but I'm not going to the proof of this closing lemma. Yeah, but this is something, if you want me in question, I can tell you, or in the proof, but it doesn't use the uniform hyperbolicity that we know. Okay, it uses something. And now, once you have this, what you do to count these plus geodetic, you just need to count these guys. So this is what you do now. I'll be very, yeah. So use the, I would just tell you, so now to count cardinality of gamma C, cardinality of gamma C of T is cardinality of gamma T, which is, these are closed geodetic, these are elements of the fundamental group. And to count cardinality of gamma C, you can see that the measure of, let me tell you, see that these sets are disjoint. So the set of gamma, this, so I'm just telling you that these sets, these guys, sorry, what do I want to say? I want to say that B intersect F minus T B, you can write it as a union of B intersect with gamma star F minus TB, where gamma is in gamma C. I'm just telling you that these are disjoint, okay? And then the measure of this, of B intersect F minus TB, this goes like, this is like the cardinality of this is like the cardinality of gamma C times the measure of one of them, okay? They don't change much, the measures, okay? Because this measure is invariant, so B intersect gamma star F minus TB. And this measure here, this is where we use product structure to say that this measure, by the construction of the measure, this is like E minus HT times the measure of B. This is where we use product structure of the measure. And this guy here is by mixing, this is like measure of B squared. Okay, asymptotically by mixing. Sorry. So this would imply that the cardinality of gamma T, I'm very rough here, is going like E to the HT times the measure of B. Yeah, and once you have this, the rest is just some analysis that, yeah. So I don't think I have much time to go into further details, but yeah. So I'll stop here for questions.
Thank you, Khadim.
Thank you.